All right, let's dive into one of the most just completely mind-bending ideas in all of physics. The theory that our entire three-dimensional universe might not be what it seems at all, that it might just be a complex projection.
I mean, really think about that for a second. It sounds like something straight out of science fiction, right? But this very question is at the core of a revolutionary idea called the holographic principle. It suggests that the reality we all experience, this 3D world, could be an incredibly elaborate illusion, a hologram projected from information that's stored on some distant 2D boundary.
So what does that actually mean? Well, you know that little hologram on your credit card, right? It's a completely flat two-dimensional surface, but when the light hits it in just the right way, bam, a three-dimensional image pops out. The holographic principle is basically saying our entire universe might work the same way. All the information that describes our 3D reality could be completely written down or encoded on a 2D surface at the very edge of the cosmos.
Now, where did this crazy idea even come from? Well, physicists didn't just pull it out of a hat. This whole thing was born from a deep, deep crisis in physics. You could even call it a cosmic crime scene. And the main suspects were the universe's most mysterious objects, black holes.
And here's the central conflict, the heart of the mystery. You've got two titans of physics in the ring. In one corner, you have quantum mechanics, and one of its most sacred, unbreakable laws is that information can never, ever be lost. It can get scrambled up, sure, but in principle, it's always there. But in the other corner, you have Stephen Hawking's work on black holes, which comes from Einstein's general relativity, and it suggested that when a black hole eventually dies, all the information about everything that ever fell into it is just deleted, gone from the universe. And that's not just a puzzle, that's a catastrophic contradiction.
So the mechanism for this crime is something called Hawking radiation. You see, over these immense, unimaginable timescales, black holes aren't totally black. They slowly leak energy, they shrink, and eventually, poof, they disappear. The huge problem is this radiation seems to be completely random, totally thermal. It carries no information about the unique things, the stars, the planets, that made the black hole in the first place. And if that information is truly gone forever, it doesn't just bend the rules of physics, it breaks them. It shatters the whole idea of cause and effect.
The first big break in the case didn't come from trying to look inside the black hole, but by carefully studying its boundary, the event horizon, the point of no return.
This timeline here shows you this fascinating total flip in thinking. For almost a century, physicists like Boltzmann understood entropy, which is basically a measure of information or disorder, as being all about volume, more room for information. Makes intuitive sense, right? But then in the 1970s, Jacob Bekenstein and Stephen Hawking's work on black holes just turned that entire idea on its head.
And this is the crucial point. They discovered that a black hole's capacity for information, it's not determined by its 3D volume at all. It's determined by its 2D surface area. Let that sink in. The maximum amount of information you can cram into a region of space isn't limited by the space itself, but by the boundary around that space. This was the first massive clue that maybe, just maybe, that third dimension we're so familiar with is, in some very real sense, an illusion.
So this area law was a huge, tantalizing clue, but it was still just a clue. To really crack the case, what they needed was a concrete, mathematical model showing how this holographic idea could actually work. And that's where a major breakthrough in string theory came in.
In 1997, a physicist named Juan Maldacena found something absolutely incredible. He discovered a perfect mathematical equivalence, a kind of Rosetta Stone for the cosmos. It connected two types of universes that seemed to have nothing to do with each other. On one side, you had a complex 3D universe with gravity, sort of like ours. And on the other, a much simpler 2D universe living on the boundary of that space with no gravity at all.
The power of this discovery is just immense. This dictionary lets physicists translate really tough problems, like the quantum physics of a black hole in the 3D world, into simpler, more solvable problems in the 2D world. And here's the truly amazing part. When the physics gets incredibly complex and messy on one side, it often becomes beautifully simple on the other. It was a complete and total game changer.
So the ADS/CFT correspondence didn't just solve a paradox about black holes. It led to an even deeper, more profound revelation about the very nature of reality itself. And this is where it gets really wild. The most profound implication is this: the fabric of space-time in that 3D universe, it isn't fundamental. Instead, it's an emergent property. It's stitched together by a purely quantum phenomenon called entanglement. These quantum connections between particles on the 2D boundary are literally weaving the geometry of the 3D world into existence.
And there's even a beautiful, stunningly simple equation for this, the Ryu-Takayanagi formula. Think of it as a direct translation between geometry and quantum information. It shows that the area of any surface inside our 3D universe is directly proportional to the amount of entanglement on its 2D boundary. Put simply, more entanglement equals more space.
A really cool modern way to think about this is through the language of quantum computing. The holographic principle acts like a perfect quantum error-correcting code. Information about any single point inside the 3D universe isn't stored in just one place on the boundary. It's smeared out, redundantly encoded across the entire surface. This is what might explain why our spacetime seems so robust and stable.
Okay, so this is all fascinating theory. It's beautiful math. But is there any actual evidence for any of it? I mean, can we actually test whether or not we're living in a hologram?
Well, the search is definitely on, and the results so far are pretty mixed. The Fermilab holometer was designed to look for a kind of jitter in spacetime, a sort of pixelation you might expect from a holographic projection, but it found nothing. On the other hand, data from the Planck satellite, which maps the afterglow of the Big Bang, is surprisingly consistent with holographic models. And gravitational wave detectors have picked up some very tentative, unconfirmed hints of echoes from black holes, which could be a sign of quantum structure at the event horizon. But you know, that holometer's null result was actually incredibly important. It didn't disprove the holographic principle at all. It just ruled out the simplest, most basic versions of it. It told us that if our universe is a projection, it's not some low-resolution, blocky image. The encoding has to be far more sophisticated to create the perfectly smooth spacetime that we all perceive. And that brings us to the final, profound question. The holographic principle completely recasts our universe, not as a collection of matter and energy moving through space, but as a vast projection of pure information. It suggests that the fundamental reality isn't physical at all, but informational. Which leaves us to wonder, if we are just shadows on the wall, what's casting the light?